Log on, tune in, find out. Another good idea from Cambridge.
And I'm looking forward to hearing about this on the stochastic diagnosis of climate dynamics and the application to sea surface temperatures, especially as I got a brief tutorial run through of it in my office the other day. So over to you, Cécile.
Thank you very much. I'd like to thank you all for coming. I'd particularly like to thank the organizers of the Newton Institute for inviting me. I'm very happy to be here. And you'll notice that I've changed my title somewhat, since I thought that the first title I gave was rather broad. It's on the stochastic diagnosis of some climate dynamics with application to tropical SSTs. And I would like to thank my partners in crime, Prashant Sardeshmukh, Lyudmila Matrosova, who no longer works with me, but I think she's much happier working in Siberia, and no, the real Siberia, and Mohammed Malik Mansour, with whom I've had many interesting conversations. And here's the nutshell of it. There's no logical incompatibility between chance and determinism. This is simply true, okay? I'm quoting directly David Ruel from his marvelous little book, Chance and Chaos, but he was quoting Poincaré in some sense. Okay, so what we're going to do is, first of all, I'm going to state a limit theorem. I'm actually going to be stating remark 8 of Papanikolaou and Kohler, 1974, and that takes 2 pages of a paper that's about this thick and practically impossible for a scientist to read, but at least it's useful to read the statement of the theorem. And I'm going to review basically the properties of a Wiener process, or Brownian motion, and talk about stochastic differential equations. And then my apologies for those of you who thought I was going to go into embedding dimensions in order to diagnose the dynamics and all of this, but basically I'm decided to confine my attention to linear systems and things that look like linear systems, okay? So some of them are not strictly linear, I agree, but this is a lot richer than you might think. And I'd like to point out the richness of multivariate systems in this talk. Please don't frown too much till you've seen it, and then you can stone me if you like. I'm going to apply these things to tropical sea surface temperatures. One of the things you can find out very quickly is if you want to be very, very unpopular with your colleagues, you come up with a prediction system that takes half a second on a Macintosh and has as much skill as a GCM. Okay, now there are things like skew and power law tails. You can use the moments, you can use the statistical properties to find out the dynamical form of the stochastic differential equation, and I'm going to go into some detail about how to do that when you can, when it works. It's like a little girl with the curl. When it's good, it's very, very good, and when it's bad, it's horrid. But we'll show you how you can see whether it's good or whether it's horrid, okay? And then we'll talk about getting the time series of the stochastic forcing, which is, of course, a categorical contradiction. Since the stochastic forcing is by definition, or not by definition, but since it is the unresolved chaotic processes, how do you think that you're going to get a time series of something that's unresolved? Well, you can get a representative time series. So the first thing is a quick review of the central limit theorem. It may not be the central limit theorem you're used to using, but what happens is you have a general 2-scale system like this. And epsilon squared g is slow, and epsilon f is fast. And what I've done here is it's not really a schematic, it's a system that I generated, dx dt versus x. And it looks like a straight line in x, a linear system in x with random scatter around it. And in fact, on the microscopic time scale, this is not random. In fact, it's perfectly periodic. However, what I've done is I've coarse-grained my system. Okay, it has a huge period, and I mean that it's products of periodic sinusoids and things like that. It's a sum of products of sinusoids, okay? But, I mean, I probably don't care whether it's the sum of products of sinusoids. So how are we going to treat this as a stochastic, and can we treat this as a stochastic differential equation? So again, this is remark 8 of Papanikolaou and Kohler, 1974, Communications, Pure and Applied Math, where you choose a scaling S. And you have this epsilon squared. Epsilon is a smallness parameter. It is not an importance parameter, okay? I mean, epsilon could be small and have a epsilon squared, and that term is still important. You can't drop it, okay? So T is time as measured in the oscillations of the atomic clock or something physical like that. And S is the time scale on which you're going to consider your dynamics, okay? So it might be seasonal time scales or weekly time scales or whatever. Okay, so now I rewrite my system dx ds is equal to, well, this is exactly the same equation I had before in the new scaled coordinates. And I'm going to consider a special case simply because it's easiest to put up on the board, that this fast term can separate into a series of systems which are resolved on the coarse-grained time scale, times things that are only dependent on time. Okay, this is a very special case. The theorem is actually more general than that, but I want to show you how you actually use this. Okay, now this has a covariance structure. And notice that what I'm doing is I'm integrating from minus infinity to infinity over the lag, and I get a matrix. And so what the theorem says is that this system here will converge weakly, and it's a weak convergence, and that's perfectly fine for us because it gives you all the moments that you would ever want, including the lag moments. The limit as this, you have a lot of the T's in the S, okay? So as the system gets more and more coarse-grained, and as, well, that's exactly what this is, then the limit of this goes to a stochastic differential equation where, note that I have the covariance structure of the rapidly varying processes in this equation. It's not just the F, okay? And I have the generalized derivative of a Wiener process. So basically what's going on is this. Could you turn on the light for just a minute, please? Okay. That's okay, you don't need to. Anyway, if these wiggles are not very big, I can basically just average it. And I get deterministic systems, okay? If I have my system coarse-grained like this, so that the correlation between this and this is very, very big, and it doesn't matter where I am in this, then I get a system with additive noise. That's where this would essentially not be able to see what the effect of X is. And if I coarse grain it at something small, let me go over here, where the variation depends more or less where I am, then I get a multiplicative noise process. Okay, so Thank you for the lights. That's why I probably shouldn't have asked for the lights to come on. And I'm going horribly slow, but this is the important thing of why we are able to use stochastic differential equations.
So, if I understand what you just said,
Mm-hmm.
in the second averaging time, which is a little broader,
Mm-hmm.
the dependence upon capital X and F is suppressed, making it additive.
Right.
And if you still have some dependence on X, then you can multiply. So both of those are contained in this.
Exactly.
All right?
Okay. Yes.
Does it matter at what rate t goes to infinity and epsilon goes to 0? Is it
You have to decide what epsilon is after the fact and see whether or not the system. What the theorem says is that there is a time scale on which this occurs. Okay, given the existence of this variance and things like that, Lipschitz conditions and all the other stuff. All right. All right. So this means. Okay, let's quickly review what this Wiener process is. Is there anyone who doesn't know what the properties of the Wiener process are? Okay.
So you've also got an alpha there, and just for my benefit, can you say what the alpha is?
Yes.
Indexing.
It's saying that this may not go to a single noise. It may actually have different noises. Okay, so the alpha, I mean, I have this sum over k, and basically I have this matrix Km, and I'm going to take this square root of this matrix. So the alpha would be the summation of this thing, which means it's not unique. All right? So that's where this alpha comes from. Ah, my pointer's running out. Oh well. Anyway, a Wiener process. Basically, a Wiener process is the generalized derivative of white noise. Okay, so this is a Gaussian random process which is zero correlated, and this is its integral. All right, so this is a Wiener process, and this is white noise. White noise has a spectrum that is flat, more or less, and the thing is that the spectrum of a Wiener process goes like f to the minus 2. All right? Now, notice that for the length of your time series, you're going to have a random walk that looks more or less like it has a... oh, thank you. Okay. I'm counting the seconds of how much I can go over then. Thank you. All right. So then, and when I'm feeling particularly malicious, I'll show this to somebody and ask, hey, pick out the dominant oscillation frequency. And a lot of times they'll find one. All right. But in fact, whenever you have a legitimately generated random walk, you're going to have an oscillation that's about the length of the time series, okay? Ah, you are kind. Thank you. So this is what a Wiener process is, and it has some annoying properties. Calculus is no longer unique. And if only one of them were found in nature, that would be fine. But there are at least two. So what happens is that, remember, our Wiener process has a mean of 0. It has non-stationary variance, and it has independent increments, okay? So what do you think this integral is? Well, remember, you set it up like this, a Riemann sum, and what generally happens where tau sub I is in this interval somewhere. With general Riemann calculus, it doesn't matter where you do it, okay? You take the limit as delta t goes to 0, the tau disappears, and you get your regular Riemann calculus. But in the presence of white noise, or in the presence of a Wiener process, these things wiggle enough that it matters. And in fact, the integral of ws dws is this thing down here. This is what you would get from regular Riemann calculus. And then you have this correction term, where alpha is the fraction from t between t and t plus delta t that tau is, okay? So if I put tau right in the middle, I get my regular calculus back. This is what's called Stratonovich calculus. And if I put it right here at the beginning, that's called Ito calculus. And physically, what that means is whether or not your system is almost continuous, but you really have uncorrelated noises, or else your system is really continuous, but you have almost uncorrelated noises. Well, the white noise isn't really white. So those limits do not commute, all right? And so what the Papanicolaou-Kohler theorem and all the other theorems, oh, forgive me, I should have mentioned Kazminski in 1966, and all of these things, those have the Wiener process occurring in the sense of Stratonovich, which is kind of a relief because that means that we can use the calculus we know and love, or don't love. But at any rate, the other point I wanted to make is that this Wiener process here is a result. It is not something that you postulate as in some of the later limit theorems that have come out since 1999, okay? Yes?
So in practical terms, are there really solid examples in geophysics when Stratonovich and Ito calculus has produced different answer?
Yes. And I'm going to show you, okay, for all of my purposes, it's the Stratonovich calculus which is important. Okay, now we go to linear inverse modeling. And this is the multivariate Ornstein-Uhlenbeck process. B has negative eigenvalues. And psi has, it may have a time-dependent variance. Okay? Notice that delta of tau has units. It has units of 1 over dt. Okay? And for now, we're going to assume additive noise, although it's probably false. I mean, all sins should be mortal. If you were brought up Catholic like I was, then you know that mortal sins mean that you know what you're doing, and you do it anyway, and no one's going to stop you. Okay? And they're the ones that send you to hell. All right? So we are going to assume that we have additive noise right now. Okay? And the corresponding Fokker-Planck equation looks like this. All right? And so given this, it's very easy to solve that the transition probability, oh, that's the other thing. The Fokker-Planck equation is obeyed not just by the marginal, but also by the transition probability. That's an important thing. Because then you can solve it for the transition probability, and you get the fact that it's Gaussian, centered on g of tau, t0. And this can be determined from the data. Okay? So you have the lag covariance matrix, you have the contemporaneous covariance matrix that you invert, and you make your forecast like that. And so the important thing about this, though, is there's a way of testing it. Because if the system is well described by a linear system, then it shouldn't matter, this B that you get shouldn't depend on the lag that you use. Okay? Now, there are some minor problems, such as Nyquist modes, that I'm not going to get into right now. But, I mean, the fact is that you have a way of testing whether or not this works. And that is important. You must falsify your dynamical model. So, the covariance matrix of the prediction errors looks like this. And after we have determined B from the covariance structure of the Green's function. We have the well-known fluctuation dissipation relationship of the second kind, for those of you who have been brought up on Kubo, that looks like that the time dependence of the covariance matrix is dependent on both the deterministic dynamics and the driving stochasticity. Okay? Well, this is nice because once you get B from the data, you can get Q from the data. All right. So let's do it. So we're using SST data. The data I'm going to show you is COADS, which is a wretched data set, but I mean, it's been redone on other data sets. I've consolidated it into 4 by 10 degree grids. I've subjected it to a 3-month running mean. This is what allows me to get away with additive noise. Okay, so I'm here. All right, if I use monthly data, weekly data, then I have to use multiplicative noise and things get much more complex. I've projected it. Is there anyone who needs a short description of EOFs? Good. Okay, it's simply a Karhunen-Loew expansion, and I explain about 2/3 of the variance. I mean, the others are indistinguishable from noise, basically. And so now my vector T represents the vector of SST anomalies, each component, or it's a vector of the principal component time series associated with these EOFs. Now, slight digression. El Nino. If I say that this, well, I'm saying that this is South America, this is North America, this is Australia, this is the Pacific Ocean, and these are normal conditions. You have your trade winds, which push the water up onto the other side, so you have your typical warm pool here, and the thermocline, which is, the temperature is basically mixed until there's a very sharp temperature gradient, after which it's very cold. And this is a very, very quick and not extremely rigorous description of normal conditions in the Pacific Ocean. But the reason it's important is because once you have very warm water here, you get convection, okay? The warm water rises, the warm air rises, it cools, it loses its water, it expels heat, it generates Rossby waves. You have Rossby wave sources, even if you're too close to the equator to have F make a difference, you get advection by the divergent flow, and Rossby waves get kicked off, and you all know about that. Well, what happens during an El Nino is that this tends to flatten, the trade winds tend to weaken, and the water sloshes eastward, taking the convection with it. All right. Again, this is a very simplistic explanation, but at least you'll know what I'm talking about if you're not used to seeing this every day. And if I subtract this from that, I get a pattern that looks like this, which is the leading EOF of sea surface temperatures in the tropical belt, okay? So notice that there's an annual cycle in this, and the red ones are warm events, the cold ones are cold events. So when this is the number of times that the absolute value of the pattern correlation goes greater than 0.5, okay? So the pattern correlation between this pattern and what actually occurred in the SSTs, okay? So this might give you the idea then that not only Q but also B should be time dependent. However, remember I said that if we did linear inverse modeling, we had a falsification procedure. We were going to look at the TAW test. This is called the TAW test. And the first thing you think about a test is it ought to fail when it ought to fail, right? So let's apply it to the Lorentz system. And so we do, and this is the expected error as a function of the different lags that we use for the Lorentz system. This is the actual error if you use it with the Lorentz system, and this looks absolutely nothing like that, and this actually does depend quite a bit on the lag you use. So it fails when it ought to fail. All right, this is nice. Expected error through linear inverse modeling to tropical SSTs, and this is using lags of 3 to 9 months. And this is actual error, and it's not exactly like, but I mean, it looks a lot closer to this than this does to this, and it doesn't depend on your lead time. Okay, about 9 months we start getting into a Nyquist mode, which means that it's like you have limits on Fourier analysis due to Nyquist problems. You have limits on pop analysis or linear inverse modeling due to Nyquist modes. And let me say right now that linear inverse modeling started with pop analysis that was published by Hasselmann and von Storch et al. And those guys at the Max Planck in 1988. Okay, but the thing is that time-dependent linear operators also fail the Taw test. Okay, you can show that rigorously. And so physically it makes sense that most of the annual cycle is going to be transmitted to the ocean by the low inertia atmosphere, okay? And rather than the sluggish high inertial ocean. And so this actually makes physical sense. All right. Well, if it's linear, where does the growth come from? I mean, if it's just an exponential, doesn't it just decay? And the answer is no, because what happens is we have the non-normality of the eigenvectors, which have different decay times and different rotation frequencies. Okay, so let's say a case where the eigenvectors of your linear operator are orthogonal. So you have A is 1 and B is 1. And A is actually the eigenvector times its coefficient. Okay, so it's just going to decay, and it might rotate. And B, we're going to say just decays. But the sum A plus B at the initial time is going to be larger than A plus B at the final time. That's inexorable if your eigenvectors are orthogonal. But let's say they're not. And you have A, and you have C, and they're both the eigenvectors multiplied by their initial amplitude. And their sum looks like this. And again, A decays and goes to A prime. And C decays, and let's just say it just decays, but their sum increases. Okay? So even though eventually your prediction must decay to 0, you can get temporary growth. And so the alignment of eigenvectors as an initial condition which gives you the maximum amount of growth depends on the lead time, and it's the right singular vector of the Green's function at tau. Okay, so we do this, and what do we get? We get this pattern preceding this pattern. It says about 8 months. In general, in physical systems, it's between 6 and 9, okay? So this is what the theory tells us. Now we have to go see if it actually occurs, all right? It's not enough to say whether or not it can happen. You have to see whether it does happen, all right? So what you see in this box is called the Nino 3.4 region. And the time series is virtually identical with PC1. PC1 has a bit more of a trend in it. And, yes?
Sorry, this optimal pattern, sorry, I don't, why is it called that?
Because this is the initial condition which gives you the greatest amount of growth at a time of, if you give it a toss. So what you do is you take the Green's function at these different lead times, and you take the right singular vectors, you know, as you march up, and generally the leading eigenvalue will go up and then it'll decay. And so the optimal one is the one that gives you the greatest amount of growth. So you get an optimal tau and you get an optimal initial condition. And then if I put this into the, if I put this initial condition into the Green's function, lo and behold, that tau time later, I get a full-fledged, mature-looking El Nino. Okay? So does it happen? Well, we resort to correlation analysis, and we get the time series of correlations with this. And we take the time series of correlations with this. We offset them by 8 months. Yes?
So in this, in this analysis, do you assume that linear eigenmodes of some underlying dynamics are the same as the EOFs?
No, absolutely not, because the EOFs are orthogonal. And I mean, if they were orthogonal, then you'd never get anything. You'd only get decay.
So when you make the reference to non-normal eigenmodes, do you have an explicit representation of that?
I do, in the sense that they're the eigenmodes of, I mean, the Cayley-Hamilton theorem tells you that G and B have the same eigenvectors, right? So, I mean, they're the eigenvectors of B and G. And you get that from the data. It's inverse model.
Have you treated them?
Yes.
Okay.
I mean, this is what you get when you do it. This is the basis for our forecast.
I thought this was EOS.
No, I just did that so that I could reduce the space. The EOFs are only a dimension reduction technique.
So this is a combination of EOS.
This is a combination of EOFs.
So it really is your dynamical eigenmode.
So it's the dynamical eigenmode. Yes, that's the important thing. Okay? See, diagnosis of the dynamics is what we're after. Okay? So does it happen? So the blue line is what actually happened up until 2004. And I'm sorry for this very, very fuzzy thing, but this is between 2004 and 2009. And the red line is the prediction, I mean the correlation between SST and the optimal structure about 8 months earlier. And the correlation is actually pretty good, even though this pattern looks absolutely nothing like that. All right? So it does happen. This was, okay, I first made this thing in 2004, but I updated it. So this is where we are on this graph right now, the correlation between the optimal structure and the temperature anomaly, and the sea surface temperature in Nino 3.4, okay? So this is where we are now, and this is where SST is predicted to be 8 months from now. So, I mean, we're predicting the La Nina to persist throughout the year.
There's a lot of spread in that.
Yeah, the correlation is only 0.65. This is the one sigma confidence interval. I wish this weren't being recorded, but this is the 1 sigma confidence interval. Okay? I don't want to talk about that right now. Okay, but these are seasonal averages. Monthly averages have more of a skew. And people like An and Jen's a convert, I think, I hope. This is why I wish it weren't being recorded. Anyway, the thing is that people have used skew as evidence for nonlinearity. And in some sense, they're right, because the skew of a linear system comes from multiplicative, correlated, additive, and multiplicative noise. And where does the stochasticity come from? It comes from all of these unresolved nonlinearities. But in the sense that your coarse-grained system looks like a linear system, you can get skew with a multiplicative noise linear dynamical system, okay? As long as you have the additive noise and the multiplicative noise are correlated, okay? As long as this G is not 0, okay? And the Green's function passes the Taw test. It's just that now B is augmented by this Stratonovich noise-induced drift. Okay, this is a case where you have a difference between Stratonovich and Ito. If you had an Ito system, this A squared over 2 would not be there. All right? And so you solve the Fokker-Planck equation.
Well,
Yes.
yes, a quick question. Is it possible to get skew by applying linear noises, but two different linear noises at the same time with different properties?
If you put the means in, but remember, we're looking at anomalies.
This wouldn't work.
I'm not willing to say it won't, but let me remind you that my central limit theorem had a sum of noises, and in fact, I mean, Q is full rank, so it has different noises with different amplitudes. It's just that it's all centered on 0. Okay. But the interesting thing about this is the PDF of the CAM noise, and it has power law tails. Well, okay, so we have a linear system that has skew. It has power law tails. And this is evidence people have been looking for to discuss is it a Levy process or not? Okay? So the question is now, is this a Levy process? And in fact, it's not. Okay. But let's look at Levy processes, just for a minute, all right? This talk is more of a random walk through some of these things. So anyway, so we're going to have a quick review of alpha-stable Levy processes. Many people will define them in terms of their characteristic function. And their characteristic function looks like this if alpha is not equal to 1, and it looks like this if alpha is equal to 1. And just to compare, here's a Gaussian with alpha equal to 2, which is a Levy process. And this is a Cauchy distribution with alpha equal to 1. And you have all of these parameters, the Levy exponent alpha, scale parameter sigma, skew parameter beta, and location parameter mu. So from now on, since people who have been studying Levy processes have been using alpha a lot longer than Sura and Sardashmukh and Sardashmukh and Sura, we're using alpha up here. I am now going to call this alpha nu. All right? It's the new alpha. So CAM noise sort of looks like an alpha-stable Levy process, but it isn't. So what I'm going to do is consider a system where I don't have the skew, okay? And I'm taking that out because I can calculate the characteristic function analytically, all right? So the characteristic function for a Levy process, I mean, the CDF of this CAM noise has a cumulative distribution function that looks like a power law tail, minus 1.4, looks like a Levy process. But the characteristic function for a real Levy process would look like that. And the characteristic process for this involves a power law times the modified Bessel function of the second kind, all right? And where now this nu is equal to b over a squared plus 1/2. I think. So let's look at these, and this is what the characteristic functions as a function of k look like. This is what the Levy process looks like, and except close to here, all multiplicative noises will have a tail that looks like a Cauchy distribution in the characteristic function space. Of course, in the parameter space, it has the same slope as the Levy process, okay, by construction. So how do you tell the difference? And the thing is that the tails are the same, they diverge as you go farther out. So what this tells you is that in order to tell the difference, you have to sample the peak of the probability distribution extremely carefully to be able to tell the difference between a CAM noise process and a Levy process. So you have the TAW test to test for multiplicative noise for the linearity system, the CAM noise, okay? You can use the TAW test, that's one thing. The other thing is you can look here, but just because you have power law tails, don't make it seem that you have a Levy process. That's the takeaway message from this. Okay. Well, let's get back to CAM noise. The thing is that there are clear relations between the moments of a CAM noise process. For example, using daily SSTs, and I was supposed to look up the data set that they use. Do you remember, Bill, what data set they use? Okay. To get the kurtosis and the skew, but this is a rigorous inequality, that the K is greater than 3/2 S squared plus R. And so this is the 3/2 S squared thing, and this is what daily SSTs do. Okay, it's actually pretty good. And the relationship between the skew and the fifth moment also seems to hold quantitatively, although I'm not sure I would actually trust the fifth moment of these observations, okay? But at least when they do it, it seems to have the right kind of relationship. But this is impressive. This is really impressive. Yes?
Okay, so that's a strict inequality you got there.
Yeah.
But the data doesn't always obey it. There are places where that inequality is violated.
I mean like this?
Yeah, not a lot of places. So I've often wondered what's the meaning of that. In the sense that they're testing a linear model here, and it's, in some sense, the departures from that is trying to tell you about the underlying nonlinear process.
I would say so, yeah.
Okay.
Yeah. Okay. Well, I told you this was sort of a random walk through stochastic processes. And there is indeed an eraser somewhere.
They're underneath the table, actually. See, I can't do the table here.
Underneath this,
Yeah, it's
okay.
all over.
All right, thanks. So what I'd like to do now is give you an example which, since we've looked at CAM noise, this isn't really CAM noise, but it is multivariate multiplicative noise. Remember that if I have a system like this, that the Fokker-Planck equation this is A squared. This is not A transpose A, okay? This is a strict A squared, which is annoying for reasons I'm not going to go into. Summation of ij. Transpose ij, ij, But I don't really care about this term, to be honest. That's why I scribbled it. The important thing is that this can completely change the mean.
This is some drift, is it?
This is a drift. This is your noise-induced drift. This is what is called the noise-induced drift. Okay? Now, what Prashant Sardeshmukh and Matt Newman and I did then is that we were saying, what does multiplicative noise do to a very simple, I'm changing gears almost completely. What does it do to a simple Rossby-Horowitz system? Okay, so we have the vorticity equation, and we calculate the steady state of it, and then we say, what's going to happen if we put in stochastic variations that are consistent with the spectrum of zonal wind anomalies? Okay, so we'll see what happens with that. And then we'll take that out of the way, and we'll say, well, what happens if we put stochastic fluctuations in the damping instead? I mean, remember, we're using a barotropic vorticity equation, so we have damping to sort of keep things stable.
Linearized or
Yeah, linearized, yeah. Anyway, so this is our stationary system. This is actually a red noise approximation. Only Prashant could have come up with something called the slow noise limit, and if you want to know what that is, I encourage you to read this article. Okay, but anyway, this is what happens to in the unperturbed system. If I put stochasticity in the background flow, what happens is that I'm going to add randomness to the phases. So I have the system advance a little bit and then retard it a little bit and advance a little bit and retard it a little bit. And so if I add up all of those, the ensemble averages is a net damping. Now, if instead I put stochasticity into the damping, a slightly stronger damping, this will, let me say that the system will react for a longer period of time to a slightly weaker damping than to a slightly stronger damping. And so when you take the average over equal numbers of stronger and weaker dampings, you get a net amplification. So if you have both of them, do they cancel? And the answer is no, because this is scale dependent and this is not. Okay? So this is an example of where the Stratanovich interpretation is important. Okay. And I just stuck this into my talk, and I know that it's sort of sticking out like a sore thumb, but from some of the questions that I had earlier this week, I decided to stick it in. Okay?
What is spatial structure in these perturbations?
Oh, the spatial structure is uniform throughout this. This is super rotating flow, and we put the we put the perturbations in the super rotating flow here, and then we took them out and put it in the damping here. Okay, so, oh, and the source is there. The Rossby wave source is there. Yeah.
You say that the stochastically damped model is rate dependent?
It's scale dependent.
It's scale dependent?
Yes, it's spatial scale dependent. Because it's dependent on the index of the Rossby mode. Okay. Now, anyone who makes forecasts knows that they sometimes bust. And so we have a state saying that the stochastic forcing giveth and the stochastic forcing taketh away. So we would like to know if we can get any type of estimation of what the time series of the stochastic forcing is. And so let's go back to our multivariate OU process, because this is where I've been, and this is where the conversations with Malik have been so important. For a Stratanovich system, the contemporaneous correlation between the noise, the white noise, and this state variable is not 0. As a matter of fact, it's a symmetric matrix and equal to Q over 2. So how in the world do you try to get a time series of this maintaining this? And the answer is actually quite easy, but it's hard to show. Well, it's not actually too hard to show. It's only approximately true, too. You estimate the time series of the stochastic forcing using a central difference. If you had an Ito system, you would have to use a backwards difference. Okay? So, but if we can get the statistics of the stochastic forcing from the FDR, why do we need the time series? And as Bill was saying, the interesting things are when your assumptions break down. And so you can get lots of really nice estimations about the deterministic system, but you would also like to know something about the forcing. Okay? So the most interesting, what's the knee-jerk reaction of any scientist given a matrix? You take its eigenvectors, all right? So you do that, and the most interesting pattern that you get is actually the third eigenvector of that Q that explains about 11% of the forcing variance.
I'm sorry, what are we looking at? This is now transition to a physical system.
Sorry. We are going back to our multivariate OU system applied to our sea surface temperatures. Now I am going to go back to the system where I got my optimal structure, where I got my B, where I got everything, and tried to forgive me, I should have said all this, and tried to get the time series of the stochastic forcing associated with that system. Thank you, Bill. Okay. So we do that. And the most interesting of the three leading noise EOFs of that system looks like this. And you look at the variance, and it seems to have a semi-annual cycle. And so you say, well, this is obvious. You have loadings in the bottom in the southern hemisphere, and you have loadings in the northern hemisphere, so it's just going back and forth, and you have a semi-annual cycle, all right? And if you only had the statistics, this is what you would discern from that. The only problem is that ain't what's going on. What's going on is this. If I actually plotted all of it, it would be going up very, very fast and have a decorrelation time of 0, or actually a month. And but if I just plot the Junes, there's a clear trend. And if I plot the Decembers, there's a clear trend. And again, I'm sorry about this fuzziness here, but this is the same kind of graph that I had. This is 2 cycles, okay? This is the variance of this, the time series associated with this pattern. And this is January, this is June, December. No, this is October. Sorry, December, June, December, June, December. Okay? Is that right? No, that's not right. December, June, December, June, December. There. Sorry. Is that clear? Should I say it again? It's 2 cycles. And it looks like there's a semi-annual cycle. Forgive me for getting confused. But what's going on is that if I separate the system into 1950 to 1975, I get only the peaks in December. And if I separate the system between 1976 and 2000, I get only the peak in June. So it seems that the well-known shift in character of El Nino in the mid-1970s may have been caused in the rapidly varying dynamics that are well described by the stochastic forcing. But this has not been established. We need to do more work on that.
Do you understand the physics of this?
Not yet.
Or
But I'm not going to waste my time looking at the deterministic part on the seasonal time scale. I might look at deterministic parts on the weekly time scale. Okay? And this is another example. I take the stochastic forcing that is forcing the, remember I can do this in geographical space too. So let's look at the North Tropical Atlantic. And what this pattern is a correlation, is the pattern of temporal correlations, contemporaneous correlations, between the time series of the stochastic forcing in the North Tropical Atlantic and sea level pressure. And using the Jung and, oh my God, I'm blanking out on their names, and I should have put it up there and I forgot. There's been this argument about whether or not the NAO has shifted east, between 1958, between the period of 1958 and 1978 and 1978 and 2000 something. So I did the same sort of thing. This is between 1950 and 1958 and 1975. And this is 1975 and 2000. And although the stochastic forcing does look like it's very, very random, that's the red block back here. If I plot only the Januaries, there's a clear trend. But I always wondered why they started in 1958. And you'll notice that I have clearly blocked out this part. So if I put 1950 in it, I don't know whether this is a problem with the data or not. This is something we're going to have to look at with different data sets, with longer data sets, with better data sets. And you still get the same general correlation patterns, but it's a lot less dramatic. And so who knows what's going on, but we clearly have some work to do with the stochastic forcing. And as you were saying, Pavel, with the physical origins of the stochastic forcing.
That data set is NCEP data set?
This is NCAR NCEP reanalyses, and these were the coads that I used, the SSTs. Okay. Notice too that this is a forcing on the SST, not the SST driving the NAO. Okay. So review. Are you exhausted? Anyway, we went through the central limit theorem a little bit, and we applied it to tropical SSTs. We did the TAW test. We showed that the non-normality of the system did give rise to an optimal structure. We looked at CAN noise versus Levy processes. In order to tell the difference, you really have to sample close to the peak of the probability distribution, and you also have to do the TAW test. We looked at noise-induced drifts, and we thought of a way of at least estimating the time series of stochasticity, and got this very unlooked for trends in the annual cycle, at least, of the rapidly varying quantities. So I think I've left myself a minute for questions. If there are any, I'd be happy to entertain them.
So the pattern of the stochastic forcing that we found, I'm trying to think about what that represents. This is an equation, this is a model that's ultimately trying to handle SST. Right? So is the noise structure then trying to tell you about heat fluxes, anomalous heat fluxes into and out of the ocean?
Well, you see, that's what we're trying to find out. I mean, because you have the...
It must be, right?
What?
Just look at it, it's Varus, and it must be a heat flux.
I think so too. And the question is how much of it is mechanical due to wind stress forcing and how much of it is heat flux. And so this is another reason why you need the time series, at least a representative time series. Okay, because if you do have a time series of the stochastic forcing, you could start then to relate it to physical variables. And the thing is that it seems like an obvious thing to do.
It's just interesting. One of them is in the North Atlantic, isn't it? One of the centers of that.
Yes,
force
can we go back to the plot?
in the North Atlantic.
Yeah, that's right.
Or no?
Well, remember-
It's not.
Yeah,
Sorry.
well, it's in the tropics, but it's in the North Tropical Atlantic. I mean, remember, this is the pattern of the stochastic forcing that you need in order to maintain the SST field. Okay? So the interesting thing to me, though, was this false semi-annual cycle.
You said that's a third one.
Yeah,
What do the first two look like?
I don't remember. The second one is very spotty. All right, it looks. I'm not sure that any of the spatial features are actually significant, but it may be. I don't know. The first one does not look like El Nino. Okay, it has some similarities to the optimal structure, but not enough for me to say, okay, this is the optimal structure. The optimal structure itself is a statistical compromise of all the sensitive regions of the SSTs. Okay. So this is actually new. It seems like an obvious thing to do, but it took me forever to show that this satisfied all the dynamical constraints that you need. Okay. So although this looks like an obvious thing to do, I mean, it was non-trivial to show that it satisfies this. I mean, I used that, you know, to show it. But, I mean, it wasn't trivial to show that this is what you need to do. And Malik's still not convinced, although he's not convinced it's wrong like he was before. All right. Yes?
Going back to the UF again, it doesn't matter whether you look at the data over the whole globe, or whether you just look at the data over the tropical Pacific or whatever, when you're trying to figure out what the noise characteristics are.
Does it matter?
Would it
A
change
bit.
your view when you-
I mean, the thing is that work by Gil Compo and Prashant Sardeshmukh have been considering the SSTs. First of all, unfortunately, you need quite a bit of data to be able to do this. And so if you've increased the number of degrees of freedom, especially if a lot of the atmosphere-ocean interaction is local, all you're doing is looking at the tropical interactions anyway. And so what addition of the mid-latitudes does is gum up the works with local stuff. All right, so yes, it does to a little bit, but not really very much. Also, as you go up farther, you'll notice that there are a lot of papers that I cited that I'm not on. This is because I was saying, it'll never work. Non-linearities are too strong up there, you know? So, I mean, my idea is that the nonlinearities might be too strong up there. If you have nonlinear advection, for example, that's important, things like that. So I don't know if I answered your question. Maybe I should have just said I don't know. But the thing is that people have done it, but they get most of their spatial patterns in the tropics.
Okay.
Did you think about applying your analysis, the whole methodology, to some sort of a dynamical toy model or GFD type? A model to which you can fit this stochastic models, but also you would be able to dynamically interpret stochastic fluctuations that you have in the patterns.
Well, yeah, I mean,
This wouldn't be
This.
real data, but you
no, I mean,
would
yeah, we actually did this to make sure that,
Yeah, along this line.
Yeah, we've done that, but remember, I don't have academic freedom. I have to make actual forecasts. So, I mean, the thing is that, you know, we try to see what's going on from an inverse point. And besides, I mean, you know, it appeals to my natural sense of contrariness to do the inverse problem. But yes, you have. As a matter of fact, I forgot to mention this. What happened was that in 1991, Alex Garcia, who is my husband, but is irrelevant for this. He's the alpha scientist in the family. We did a molecular dynamics simulation, okay? And what he did was that he did it in a Rayleigh-Bénard configuration, where you had the thermal boundary conditions on the top and the bottom and elastic boundary conditions. Forgive me for saying slip before. They were elastic boundary conditions on the side. And he would run the molecular dynamics simulation, first in equilibrium. Let me put this down so I'm not. First in equilibrium, and then in a system where you had very close to the critical point for Rayleigh-Bénard convection, okay? And he put it into little subvolumes, and in each subvolume, he gave me a time series. He sampled it every, I think it was 10 collision times, and the subvolume was something like 10 mean-free paths or something like that. All right, so then he gave me the UVW in local equal partition. He gave me the temperature and the number of particles in each time, okay? And then I did limit it. So what do you think I got? All of you who heard me talking about this Monday, just be quiet. What do you think I got?
So you fitted stochastic model. Is there?
Yeah, the linear.
And it worked.
Yeah, guess what we got?
So did your stochastic model reproduce the patterns?
We got the Navier-Stokes equations, okay, including, because of the Q, the dependence of the stochastic terms on location. I mean, we basically verified the 1954 Landau-Lifshitz theory, okay, of how the fluctuating Navier-Stokes equations should look, you know, due to the fact that you had individual molecular collisions. But the important thing was that we got it to work very close to the critical point, too.
So you're saying you fitted your stochastic model to kinetics?
Yes.
And you got the fluid dynamical?
Yes.
In there? Wow.
Yeah. That's JSTAT Phys 1991. Garcia and Penland.
Okay, I think we should break the coffee in a minute, but I'm going to take Chair's privilege just to ask, are we effectively now, from your work, in a position we could say we should be monitoring these regions if we're, for example, concerned that there might be a future regime shift in ENSO or whatever people describe it, the 76 centered changes? I mean, can we operate, in a sense, can we use this kind of work, is it at the point we can use it to think about some early warning monitoring? Or
If truth be told, I don't know. One thing.
what should we be monitoring, shall we say? You sort of show some regions we should be monitoring, and we had a little bit of discussion about what exactly physically we should be looking at as the source of this
I know.
stochastic forcing.
And I haven't actually thought about it for a long time in terms of regime shifts. I've only been thinking about it since Monday.
Right. Very good. Something to think about over coffee or tea.
Okay.
Thanks, Cécile.